Good afternoon, everybody. Today I discuss the topic fundamental concept of stoichiometry, mole concept, and chemical process calculation. Now, the word stoichiometry has its own origin from Greek word stoichein, that is meaning elementary constituents, and metren, that is to measure. The conventional meaning of stoichiometry um, tells that the limitation of calculation involving involving the quantities of material involved in chemical reaction. But in chemical engineering, it is used in the stoichiometry term is used in broader sense, and it is also involve the calculation of behavior of gas and gas mixture, phase behavior of liquid and solution, and material balance and energy balance in unit operation and processes. Now, coming to the chemical reaction and process calculation. The conversion or transformation of raw materials into products takes place in a chemical reaction. For solving the material balance and energy balance problem involving chemical reaction, it is essential to write a balanced chemical reaction. Now, say for example, the iron pyrites oxidation reaction with air to produce sulfur dioxide. So here we have written the balanced chemical reaction for FeH2 iron pyrites. 4 mole of FeH2 plus 11 O2 gives 2 Fe2O3 plus 8 SO2. So, to describe this stoichiometry equation, to describe this balanced equation, we need to describe the two terms stoichiometric coefficient and stoichiometric ratio. The stoichiometric coefficient is the coefficient of chemical formula of different species in equation, and stoichiometric ratio is the ratio of stoichiometric coefficient of any two substances. The stoichiometric ratio helps to calculate the number of moles of substances involved in chemical reactions. Now, what we can tell from the from the above equation, iron pyrites oxidation reaction. 4 moles of FeS2, that means 4 into molecular weight of iron pyrites, that is 479.9 kg of iron pyrites reacts with 11 moles of oxygen, that is 11 into molecular weight of oxygen 32, comes 352 kg oxygen, and produces 2 moles of Fe2O3 ferric oxide, that is 2 into molecular weight of ferric oxide, it comes 319.38 kg, and 8 moles sulfur dioxide, that is 8 into 64, that is molecular weight of sulfur dioxide, it comes 512 kg sulfur dioxide is produced. Now this ratio of the ratio of reactants charge 4:1, that is ratio of iron pyrites and oxygen is to oxygen, that is 4:11, in the mole basis is the stoichiometric ratio of this chemical equation. Now come to the excess and limiting reactant. Excess reactant is actually in practical industrial process. One of the reactants is supplied in excess to the stoichiometric requirement to ensure the completion of reaction, or to prevent the occurrence of side reactions, undesired side reactions. So the excess reactants presents not in the stoichiometric quantities. It is present in the reactant mixture in the excess to stoichiometric requirement. Limiting reactant present in the least stoichiometric proportion. Limiting reactant will disappear first from the reaction mixer, and it determines the amount of product obtained from the given reactant mixer or feed mixer. Now, how to determine the limiting reactant and excess reactant in a given reaction? Now we consider the synthesis of ammonia reaction. Synthesis of ammonia is represented by the chemical reaction nitrogen plus 3 hydrogen, that is N2 plus 3 H2 gives 2 NH3. If here it is given, if ammonia converter is charged with a mixture of nitrogen and hydrogen containing 20% nitrogen by volume, which one is the limiting reactant? So you have to find the limiting reactant. The reactants in stoichiometric quantities of the ammonia synthesis reaction, that is the ratio of moles of hydrogen to moles of nitrogen is 3:1, and in the given feed mixture there is 20% nitrogen present. So if we consider 20% by volume, and it is same as the 20% by mole, so if we consider 100% is the total mixture, then 20% nitrogen, 20 moles of nitrogen and 80 moles of hydrogen is present in the feed mixture. So the mole ratio of hydrogen to nitrogen will be 80:20, that is 4:1. That means for every mole of nitrogen, 4 moles of hydrogen is supplied to produce ammonia, 1 mole ammonia. To produce ammonia, and which is this ratio 4:1. This ratio is excess amount of this is actually, this is 4:1. This ratio is higher than the stoichiometric ratio. So hydrogen is excess reactant. Hydrogen is used in excess amount to stoichiometric requirement. Therefore, nitrogen is limiting reactant and hydrogen is excess reactant. Now, if more than 2 reactants are present, one of the reactants may be chosen as reference, and the ratio of moles of each reactant to the moles of reference substance is calculated and compared with respective stoichiometric quantities for finding out the limiting reactants. So percent excess, for the excess reactant, percent excess is calculated as excess amount divided by theoretically required amount into 100. Now, how to calculate percent excess? Say for example, the pyrites oxidation reaction, 500 kg of pyrites is oxidized in a supply of 400 kg oxygen. So we take the balanced equation of pyrites oxidation, and then we calculate the stoichiometric requirement of oxygen to react with given feed 500 kg of pyrites. That is 352 divided by, that is the amount of oxygen required stoichiometrically divided by amount of pyrites reacts with the oxygen, that is 479. It is described earlier how in amount is coming. So for 352 divided by 479.9 into 500, it is coming 366.7 kg. So the stoichiometric requirement of oxygen to react with given feed 500 kg pyrites is 366.7 kg, as oxygen supplied for oxidation reaction is 400 kg. So it is greater than the theoretical requirement, and so oxygen is in excess amount and pyrites is limiting reactant. Okay, so percent excess oxygen percent excess oxygen supplied for burning of pyrites equal to excess amount divided by theoretical required amount into 100. So 400 minus 366.7 divided by 366.7 into 100, that is coming 9%. And you can calculate alternatively by considering the kilomole basis. Kilomole of oxygen required theoretically, and kilomole of oxygen supplied in the feed mixture. Now we can solve one problem for clear to calculate the excess reactant and limiting reactant. And so the problem is formation of phosgene. Carbon monoxide combines with chlorine in the presence of a suitable catalyst to form phosgene. According to the reaction, carbon monoxide plus chlorine gives COCl2 phosgene. After reaction, the products obtain 12 moles of phosgene, 3 moles of chlorine and 8 moles of carbon monoxide, assuming that the original reactant mixture is free from phosgene. Now calculate the percent excess reactant used. So your stoichiometric equation is CO plus Cl2 gives COCl2 phosgene. And now your product after reaction, your product mixture is given, that is product contain 12 moles phosgene, 3 moles chlorine and 8 moles carbon monoxide. Now according to the stoichiometry of the equation, it can be said that to produce 12 mole phosgene, 12 moles carbon monoxide and 12 moles chlorine reacts. So therefore original reaction mixture contain 12 plus 8 moles, that is 20 moles carbon monoxide, and 12 plus 3 that is 15 moles of chlorine present in the original reactant mixture. Now the stoichiometric ratio of reactants. Carbon monoxide is to chlorine equal to 1:1. The ratio of carbon monoxide and chlorine in the given reactant mixture is 20:15. That comes 1.33:1. So this ratio is higher than the stoichiometric ratio, and it can be said that chlorine is the limiting reactant and carbon monoxide is the excess reactant. Now percent excess reactant used you have to calculate. So percent excess uh, percent excess of carbon monoxide. Carbon monoxide is the excess amount. So percent excess of carbon monoxide is calculated as excess amount, that is 20 minus 15 divided by theoretically required amount, that is divided by 15 into 100. That will come 33.33%.